Okay, I think it's all. Okay, I think it's already 2 p.m. over here. So, ladies and gentlemen, good afternoon and good morning for Dr. Yimin Chao. Assalamualaikum warahmatullahi wabarakatuh. First of all, I would like to welcome you all to this webinar series organized by Jurnal Kimia Sains and Aplikasi, Departemen Kimia, Universitas Diponegoro. And the title of today's webinar is Desperately Seeking Silicon for High Capacity Batteries, which will be conveyed by Dr. Yimin Chao from East Anglia University, UK. And before the presentation begin, allow me to introduce the speaker. And I will share this screen maybe, yeah. Okay, this one. Okay. Yeah. Okay. Dr. Yimin Chao, Head of Nanomaterials Innovation Lab, Leader in Nanoscience, School of Chemistry, University of East Anglia, Norwich Research Park, Norwich, UK. And then the academic qualification, he got his PhD in nanosciences from Newcastle University in 2004 with a thesis title Electronic and Optical Properties of Nanostructures Material. And the professional qualification, Secretary of Royal Society of Chemistry from July 2021 to present, and then Treasurer in Chemical Nanoscience and Technology Group, Royal Society of Chemistry from February 2016 to July 2021, and then the PhD thesis examiner in Newcastle University since 2014 to present, and then postdoctoral research fellowship at the Wolfson Chemical Nanosciences Center at Newcastle between 2004 and 2007, and then as a UEA staff start from 2007. Okay, and then his publication, for the total paper publication is 19.3, and then it's index 21, and then the total number of citation is around 1,695. And then the research area or research interest is investigating nanostructure system from the basic physical and chemical mechanism of synthesis through their optical and electrical properties to energy conversion, energy storage, and biomedical applications. Also, current research themes include functionalization and characterization of silicon quantum dots, biomedical application of silicon quantum dots in targeted and monitored drug delivery, and application in lithium-ion batteries and thermoelectric modules. So this is Dr. Yimin Chao profile, personal profile. And then before we start, in order to avoid any disturbances during the presentation later, I would like to ask you all to change the mode of your Zoom media into mute. And then moreover, if anyone has question, please write it down in the chat room or menti.com with specific code. We will share the code later on. So thank you very much. And then now the time is yours. Dr. Yimin Chao, you have 40 to 45 minutes to present. And then after that, 20 to 30 minutes for discussion. Okay, now time is yours.
Right, okay, let me just share the screen.
Yeah.
Okay. Can you see my screen now?
Yes, we can see.
Yeah. Right, okay. Great, okay. So good afternoon, everybody. So it's my pleasure to give this webinar here. So today's topic is I'm going to look at the research currently I'm doing in the lab, and also I'll talk about a bit of history of my research. Basically, in the past 20 years, my research is focused on silicon nanoparticles and their applications. Currently, we are looking at the applications in lithium batteries. Okay, so I think my research will have some contributions to UN Sustainable Development Goals. So basically, my research is related to number 7, affordable clean energy. Obviously, when we talk about lithium batteries, it's about battery energy storage. So that's related to the clean energy and affordable energy as well. Obviously, this week, IPCC published climate research report. So obviously, clean energy is related to climate actions. And I'll talk a bit about health-related topic as well. So yeah, I'll briefly point it out. This battery research is related to that as well. Okay, so probably everybody knows now global market for the electric vehicle is huge now. It's over 110 billion market, but by 2027, this market is going to reach over 500 billion pounds. So it's really a growing fast market, and it's a bigger market as well. And the UK government also set up a zero emission strategy that requires all the vehicle in the UK becomes electrified by 2030. So that means by that time, we are not able to buy any vehicles using petrols or diesels. So that's really not too far away now. So it's within 10 years' time. So it is an urgent task for everybody. And this topic also related to the current hot topic about circular economy. So that's another issue. I'm not going to spend the time to look at that now, but if you're interested, I can explain that later a bit. Okay, so let's look at the current programs related to this research. So everybody knows, so electric vehicle, that's the future, or it's not far away. So I think in the market, some of you already have this kind of car, but the problem is the driving range. It's not too far away. It's not very convenient. So usually if you have petrol car, diesel car, after you filled fuels, and then you can drive over 500 miles or something, and then you don't need to recharge your car very often. And also currently the price is another issue, but technically, from our research point of view, in this kind of car, there's a battery weight over 600 kilograms. That's really a big issue. So usually your fuel tank, that's 60 liters or something. So maximum 60 kilogram or something. But for electric vehicles, you have to put very heavy batteries in your car. So that's really a bigger problem. So we need high capacity batteries to solve this problem. Say if we have capacity 10 times better than current batteries, and then you can reduce that battery to 60 kilograms. So that would match the current your fuel tank weight. Okay, so that's one research focus. Another point at the moment, as I promised, I'll mention a bit about health issues. So some older people need this pacemaker. So if you have pacemaker now at the moment in the market, usually using primary batteries. So all these primary batteries, you can't recharge them. Once you put that in, and then if the batteries run out, and then you have to send patients to hospitals to replace them, and that means you have to make another operation and replace the pacemaker. And so that's from doctor's point of view, that's really life-threatening infections, etc. So put the patient at risk. And as for some patients, and they in their lifetime, they need the multiple operations. So that's really a bigger risk for patients. So if we can have long lifetime batteries, and if we have high capacity batteries, so people can just recharge them, don't need any further operation to replace them. And if you have high capacity batteries, so they don't have to recharge the battery every day. Okay, so think about with this pacemaker, if you have to recharge them frequently, that's another big issue. So we need high capacity batteries. Okay, so from these examples, we know we desperately need high capacity batteries. Okay, so look at the high capacity batteries, we need to look at the materials. Okay, so from this table, you can see if we make a comparison for our anode materials, let's say silicon here, yeah, theoretically, silicon has the theoretical capacity over 4,000 milliamps hour per gram. Okay, so that's the best one from this point of view. So currently people using carbon as the anode materials. Okay, so that's the conventional batteries in the market. So the capacity is over 300. But if we replace that carbon with our silicon, okay, so in theory, you should be able to improve that capacity, yeah, by 10 times. Okay, remember I said currently in the electric car, you have 600 kilograms batteries. So if we have 10 times better capacity, and then we can reduce that weight to 60 kilograms, matching the current petrol cars fuel tank weight. Okay, so yeah, so if you just look at this data in this table, and then you have got a clue. So if we can replace carbon with our silicon, and the problem is sorted. okay? But I have something here. I'll come back to this table a bit later. So from this point of view, you might think, okay, that's ideal situation. So we have this battery and we have a silicon anode, and capacity is really high, 10 times better than carbon. And then say for current battery research, usually people looking at cathode materials as well, and they look at electrolyte. Electrolyte, currently people using a liquid electrolyte. So there are some safety issues. Last week in the news, there's a big fire in Australia. Say that's the Elon Musk's big factory. So the fire with the batteries. So that's another safety issues. So talk about solid electrolyte. Okay, so with all these together, the problem sorted. But when we talk about replace carbon with our silicon, so there is another problem, okay? So during the charge-discharge cycles, and if we just using silicon, and you will see some cracks and fractures after a few cycles, okay? So that's the problem with silicon. So let's go back to that data. Okay, so basically you have this theoretical high capacity, but the problem with silicon is you have volume change, very large volume change during recharging cycles. Okay, so that's the problem with silicon. Okay, so how to solve this problem? Okay, so as you know, in my research life, I really dedicated to silicon nanoparticles. So look at the size. So for bulk silicon, obviously you have this kind of cracking fracture problem during the charging, discharging. So if we reduce the silicon size to nanoparticles, okay, let's see if the silicon nanoparticle size lower than 150, or usually in my lab, we working with silicon nanoparticles in a few nanometers, okay? So you reduce the silicon size to nanometer scales, and then during charge and discharging, you won't see these cracking or fracture. Okay, so that's the way to solve this. Okay, to avoid these cracking, fracture, we're using nanotechnology to produce silicon nanoparticles. And once we have this problem solved, and we can get high capacity batteries. Okay, so looks like this is the solution for this high capacity batteries. Okay, let's talk about our research experience. Okay, so remember, we need the silicon nanoparticles. Okay, so in the past 20 years, I really focused on silicon nanoparticles. So a bit of history. So stage one, we synthesize silicon nanoparticles using top-down route. Okay, so that's my first stage research. So in that time, that's about 20 years ago, when I started my PhD research in Newcastle University. So we started to synthesize silicon nanoparticles. So basically in that time, we're using top-down method. So what we did is we cut a silicon wafer to this kind of silicon chip and then put in the electrochemical etching, and then we can have this kind of porous surface. So once we have this porous surface, basically on the surface, we have this kind of surface. So some sizes are still big, somewhere we got small size silicon. And if we put that in some reactions, say put in the alkene solutions, and then we can grab these bits off, and then with some purifications, filtrations, and then we can have these small sizes silicon particles. Okay, also capped by some other functional ligands. Okay, so then we, and once we take this off, so we get silicon nanoparticles. So that's the top-down method to produce silicon nanoparticles. Sometimes we call that silicon nanocrystals or silicon quantum dots. Okay, so let's have a look what we got. Say the first step, we after the electrochemical etching, we have this kind of silicon, porous silicon surface. So these are SEM images on the cross section. Okay, we can see these kind of channels. Okay, so that's the different scales. Say this one is 1 micrometers, but this is 500 nanometer scales. So from these images, you can clearly see the channels. Okay, and if we see, take a topo view, and you see this kind of surface. Okay, that's a very a nice silicon, porous silicon surface with all these channels. You see some from top view, you see these channels from the top, and from cross section, you see these vertical cross section channels very clearly. Okay, so yeah, if you interested in these kind of data, you can go to the papers we published. Okay, so that's the first step. And then afterwards, we try to functionalize the surface. So as you know, after the etching, you see this kind of hydrogen terminated surface, but these surfaces are not stable. So we need to protect the surface. Okay, and then we use different ligands to do it. So one example here is using amine to protect the surface. And the purpose for this one is we try to get water-soluble or hydrophilic surface for silicon nanoparticles. We did a lot of work for drug delivery and diagnosis applications. So that's one example here. And also on that surface, we can functionalize that further with sugar or other ligands. Okay, so these just some examples we did in the past. And a recent example is we using thiourean to cap that surface. So all these sugar or thiourean, these kind of work, first of all, try to protect the surface. Second is try to get some function on the surface. So thiourean is one of the drug as well. So these are just examples. So basically, we have this kind of surface with either hydrogen terminated or amine terminated, and then we can easily put other functional group on the top. So for drug delivery or other diagnosis applications. Okay, so these are some designs and examples. Basically, after the synthesis, we needed to characterize the materials as well. So for example, we use XPS to look at the surface, look at the materials we synthesized. So that's typical surface. So we have silicon is the main materials, and then obviously we have oxygen, carbon, and to say if we have amine capital, we have nitrogen on the surface as well. So XPS is one typical method we could use to characterize the materials. Okay, so let's just show you one example how to characterize the surface. Okay, so that's the first stage. We use a top-down method. The problem is top-down method, we can easily generate silicon nanoparticles in milligram scales. So for research skills in the lab, that's we played with that. We got very excited experience on that. We published a lot of beautiful work, and so that's very nice. But the problem is for industry scales, we really need materials in grams, kilograms, or even pounds. Okay, so top-down method, we can easily get milligrams. Play with that in a research lab, that's really nice. But for industry applications, it's not good enough. Okay, so that made me move on to stage 2. We use bottom-up method to scale up the materials. Okay, we need grams, kilograms. So here I'm going to talk about one example. We did a bottom-up method to produce grams, kilograms for one company. The company using the materials to do thermoelectric modules. So thermoelectric, basically people probably know that, can use that to convert waste heat to electricity. So I'll touch a bit on that later. Okay, so one example here is, this is one of the reaction scheme. So use this bottom-up method, we can get a phenacetylene cap the silicon nanoparticles. So this is a bottom-up method. So basically you just scale up the reactions from the lab to industry, and then you can get kilograms, tons of this kind of materials. Similarly, we have ligands protected silicon nanoparticles, and we can use different functional ligands to do this kind of work. Okay, so that's the second stage we use to scale up the productivity. Okay, I'll talk about a bit characterization again. So after the synthesis, we need to merge the size of the materials as well. So here for the bottom-up method, we really need to confirm whether silicon nanoparticles, they are still got crystalline structure inside. Okay, that's important for our applications. So we look at TEM and then confirmed that structure still got this kind of crystalline structure, and the size that's within a few nanometers. So and size distributions are really important. Okay, so so we use DLA's TEM to measure the size as well, and also we got this high resolution TEM. So you see different nanoparticles or nanocrystals on this on one images. So that's very rare image in under TEM. Usually, if you people, if you look at the published papers, you see these kind of images and just catch one nanocrystals. So that's usually people publish in that way. But in our lab, we got this very variable TEM image. We see these nanocrystals, multiple nanocrystals from one image. Okay, so talk a little bit about thermoelectrics. So what thermoelectric device do is this thermo Seebeck effector. So with temperature gradient, so with this thermoelectric materials, we can generate voltage. So that's a Seebeck coefficient. And how to evaluate this kind of materials, we use this ZT, figure of merit, to describe the materials. Okay, so that's a Seebeck coefficient. So, and C gamma here is electric conductivity, kappa is thermal conductivity. So just to describe the materials using these ZT values. So higher ZT values, the better thermoelectric materials. Okay, so obviously with this thermoelectric materials, they can convert waste heat to electricity. So waste heat means you can have this temperature gradient, and then you can generate a voltage. So that means you're using waste heat to generate electricity or convert. Usually I using word convert rather than using generate. Okay, convert heat to electricity. And then these applications got really a lot of fancy applications. Say people can put that in current vehicles. Currently people's majority in the market are still petrol, diesel cars, and then the high temperature in the exhauster, and so can convert that waste heat to electricity for the car to use, and also can use your body temperature to convert your temperature to electricity for other device to use, say wrist watch. That's one example, and some other applications in military applications. This is submarine. Submarine means you need to go to somewhere very quietly rather than make any noise. So another applications in the spacecraft. So using radiation to generate electricity. So this is one example. That's a spacecraft Cassini crashed to Saturn. I think that's in 2017, after 20 years in the space. So think about this spacecraft in the space. They run that without any sunlight. So how to provide the energy there? So basically, say this one in the space run over 20 years. So from Earth's here, Saturn's here, and you have spacecraft here, and then So how to provide energy or supply energy, that's a big issue. So what that Cassini did is using the radiation to generate electricity, basically using this thermoelectric generator to generate electricity. Okay, so that's the applications. Let's focus on the materials again. So as I said, we need to look at high ZT values for these materials. Okay, so I look at this thermal conductivity and electric conductivity. So to improve that, okay, you can either reduce kappa, increase sigma. Okay, so as I said, I really dedicated to nanotechnology. So I looked at this problem and then made this consideration. So if we reduce materials, reduce the size to nano size, okay, and then we can still get let electron transmission transport still on. So that means we can still keep this electric conductivity, but reduce the size. That means you can block phonon. Block phonon, that means you can reduce kappa. You reduce the kappa, and then you can improve this ZT. Okay, so that's the theory. And we also did an experiment in our lab. We made a comparison with different size of our silicon nanoparticles and compared with bulk materials as well. So obviously that thermal conductivity significantly reduced. Okay, so yeah, that's theory, right? And we confirmed that with our experiment. Okay, so we did the work, and then obviously our idea is still using our silicon nanoparticles. So some other groups did that with silicon nanowire. Okay, in theory, both are working well, but in practice, I prefer to use silicon nanoparticles. Think about silicon nanowire; they are really fragile, so it's difficult to manipulate. But nanoparticles, it's easy to handle. Okay, so with that progress, we really did, and then we achieved the ZT about 0.6. In the market level, it's 1 at the moment. So we are really made the materials comparable to the market levels. So that's why the company in the industry sponsored our research in this project. Okay, so that's the history. Now let's move on to the solutions for high capacity batteries. Okay, so yeah, so the previous two stages are really made my research today and to step into this battery research. Okay, so still looking at this focus on silicon, and as I explained, we need silicon nanoparticles rather than bulk silicon, and bulk silicon wouldn't work in these anode materials. Okay, so we know silicon got very high capacity, but we really need to use proper the size of silicon rather than just use bulk silicon. Okay, so that's our current stage. Look at silicon nanoparticles application in high capacity anode. Okay, So our solution one is we still, using silicon nanoparticles. Probably up to now, you understand it's easy for us to produce or synthesize silicon nanoparticles in our lab. But to look at the anode applications, obviously we still need to consider other issues. So so basically we can just use silicon nanoparticles, but to make that work well and to make that useful in anode within lithium batteries. So we did that using this route. So basically we use some titanic oxide layer to protect them. Also, we had various stages to make the materials really work in anode. Okay, so just show you some results here. So after the synthesis, obviously, as I said, we really needed to characterize the materials. Okay, so that's SEM images. We see these kind of spherical shapes, really silicon nanoparticles encapsulated by this is from titanic oxide encapsulated silicon nanoparticles. And also we use XRD to confirm we have silicon, carbon, titanium, all these within our materials. And again, we use XPS to characterize the materials. Okay, so all these are general routine characterization method for materials. So here's just some examples. Okay, and the performance-wise, we put these materials. We assembled the materials into batteries. And with half battery, we measured, we tested cycling performance. And here is one example, run up to 100 cycles, and we can easily get a stable capacity over 800, okay? So 800, 900. And the initial capacity, obviously, that's higher. So if you still remember, in that data table, the theoretical capacity for silicon, we should be able, should have over 4,000 milliamps hour per gram. But in reality, okay, if we can achieve something around 1,000, that's really good enough. Okay, remember theoretical value for carbon, that's 376 milliamps hour per gram. But in reality, in the lab, usually we can, when we measure that, the capacity is really low. So if we can get to 100, that's really good batteries already. So think about, we can achieve 800 capacity here. That's really good results. Okay, so that's one solution, or solution one from my lab. Okay, but still remember, we use artificial silicon nanoparticles. We synthesized silicon nanoparticles. Remember, all these nanotechnologies are very expensive. Okay, so that made me to think about another solution. Okay, we use natural materials rather than artificial nanoparticles. Okay, so solution one is really expensive. Okay, and in my opinion, it's not sustainable. It's not with current circular economy. Okay, so here is the solution two. We use biomass. Okay, so here it's I think that's either rice huskers or barley huskers. Okay, all are natural materials. Using natural materials, we process the natural materials in the lab, and then we get silicon nanoparticles. Okay, remember in the nature, silicon nanoparticles everywhere. Okay, so I can show you some data here. So basically, let's say take a rice huskers or barley huskers, and we measured that, analyzed that in the lab. We confirmed we can have 14% of the materials are silicon nanoparticles. Okay, so that's really good enough. Okay, so silicon-rich materials, okay, biomass or waste from nature. Okay, we process them. Okay, so also this solution, as I said, we need to think about the industry scales. We can make grams, kilograms, tons. Okay, so in this solution, we don't have any limitation. Okay, we can easily make grams, kilograms, tons on that. And also these materials and these resources, such let's say take example from Scotland, the Scotch, that's really a big industry, and then they got all these kind of waste, so we can just use it to make it useful for battery materials. Okay, so we confirmed that's silicon rich in the materials, and then we also measured after process. We confirmed they got silicon, and obviously you got carbon as well. We need carbon in the anode, and using XPS as well. And obviously we can easily measure that with SGM, EDS, etc. Okay, so that's just a general materials characterization. And then afterwards, obviously, we needed to see the performance. Okay, so we measured cycling again. Yeah, we got similar results. So we can have something still around 800. That's really a same level, similar level as our artificial silicon nanoparticles. So remember, as I say, the solution one, that's a typical nanotechnology-based artificial materials. They are very expensive, but solution two, we use waste biomass and cheaper, and this solution or this procedure, it's also environmentally friendly. I call this is green method. Okay, so we achieved the similar level of the performance. Okay, so here's another data. We just compare the different process. Say we use nitrogen doping or without doping. We use ball milling or without ball milling. Obviously, without ball milling or without doping, the capacities are low, and if we need the ball milling and doping to process the materials to achieve better results. Okay, so that's just something, another parameters. So if you use different processing temperature, etc., and then that would affect the final performance as well. So just some different parameters during the material processing, this kind of stuff. Okay, so yeah, that's our best results at the moment in the lab. So okay, so I think I'm cautious on time. So I should just summarize this talk. So just showed you some different synthesis methods and for functionalization for synthesize nanoparticles, and silicon nanoparticle based materials we really processed in the lab, and now we confirmed, or I hope I convinced you these are useful materials for high capacity batteries. And yeah, so the point here is we're using biomass to do the work, and then these are really got a potential impact on energy storage, on circular economy, etc. Okay, so finally, I just try to thank all my people and the funding bodies to support my research in the past decades. And thank you very much for your listening. Thank you.
Okay, thank you very much for the presentation, very great presentation from the challenge and then the solution 1, second, and then third one. So we are going to move to the discussion session. So here is the sum of questions from the participants. Can you see?
Yeah, I can see that. Yeah.
Okay, maybe. Yeah. Okay. Yeah. First one, what is the minimum specific capacity value for good battery? Because in the first presentation, you present the specific capacity of some materials. Okay.
Yeah. Yes, that's a very good question, actually. Yes, I briefly mentioned that. Currently in the market, the conventional batteries, they're using carbon. So for carbon, the theoretical capacity, that's a specific capacity is 376. Yeah, as I mentioned, in the lab, when we try to measure them, that's about 100, that's at maximum. So yeah, to answer this question, well, yeah, obviously for good batteries, you put that condition as good battery. Good battery, obviously the higher specific capacity, the better.
Okay.
Yeah, no minimum values for that. But I just tell you in the current market levels. Yeah, if you think 100, that's the market level.
Okay. Okay. Next question, Mr. Adi. Okay, why does volume change during charge and discharge processes? I mean, well, in your presentation, you said that lithium has a very high specific capacity, but in this case, yeah, it has what is it? Challenge in change of the volume. Okay.
Yeah. Okay. Yeah, that's a very good question, actually. Yeah. Okay. So yeah, if that's the conventional materials, say bulk materials, basically think about the charge discharging. So the battery works when the lithium ion, during the charging discharging means you insert lithium ion into your anode and then release. Okay, so insert and then release. So that's the charging discharging process. So that's how the battery works. Okay, so think about a bulk material. So you have ion insert into your structure. Obviously, when during the charging you insert the lithium ion into the materials, obviously you will see volume changes. Okay, so for silicon, because silicon can accommodate more lithium ions, that's why the specific capacity is higher. Okay, so you insert more lithium ion in, and obviously you will see the volume changes. Okay, for any materials, so during the charge and discharge, also you see the volume changes. But for silicon, you got the maximum volume changes. And for our technique, so using silicon nanoparticles, so that means lithium ions, when you insert to anode, so basically lithium ions can just accommodate them on the surface rather than into the bulk structures. So that could solve this problem.
Okay. Okay, thank you. Next question. What I understand is that silica compounds have low flexibility and ductility. Doesn't it cause LESE to be easily damaged?
So yeah, that's a similar answer to the last one. So basically, yeah. So if that's a bulk structure, you try to accommodate more lithium, and then obviously it can easily damage the crystal structure. So that's a similar answer to the last one.
Okay.
Yeah.
Okay. The next, the use of organic compounds in the silica organic complex, will it produce a material with high stability? Are an organic compound easily degraded?
Yeah, this is a very good question. Yes, so we use some organic ligands to protect the silicon surface. As you know, if that's just hydrogen terminated the surface, very easily to get oxidized. So with these organic ligands, you can protect the surface. So yeah, that means these materials that's more stable, and then the materials without protection. And degradation, yes or no. So depend on. Yeah, we investigated this as well. So yes, so some materials, yeah, some compounds got easily degraded, but you need to choose the compounds carefully.
Okay. The next one. What is the relationship between porous silicon with capacity of battery? Maybe because maybe some papers said that porous is very important for battery, I think. Maybe you can explain it.
Yeah, it is. Yeah, the porosity is a big issue for capacity of battery here. Yes, so yeah, I just try to explain the concept in a very easy way, a simple way. Say, if you just use nanoparticles and you got very high surface to volume ratios, and then yeah, obviously in reality, probably you for the natural materials, you might have some porous silicon or mesoporous particles rather than in the real nanoscales. Yeah, so in that case, the porosity is really important. Yeah, if you just understand in a very simple way, yeah, let's put that in a simple way. Yeah, you got more high porosity, so you have higher surface to volume ratio, and yeah, you can think yes, you have better or higher capacity. But that's just in a very simple way to understand that. In reality, really, I got loads of issues you need to think about.
Okay, next question. What is the main purpose of introducing functional organic ligands around silicon? Does it will make silicon become more porous and leading to a weaker durability?
Yeah, as I explained, so two purpose to introduce organic ligands on the surface. One is protect it. Second is, as I said, we played a lot with functions. Say you can directly use some drug ligands to link with silicon surface, and then so you can do drug delivery. So that's two purpose, main two purpose. Make more porous. No, that wouldn't change any porosity, and durability, stability. Again, that's depend on the ligands and the synthesis procedures.
Okay, next question. As we know that one of the weaknesses of silicon in battery application is the volume change during lithiation, and delithiation lead to pulverization. Maybe next question, the next one, Adi. Oh no, the previous one. I don't know what is the question actually, the previous one. Mr. Adi, the previous one? Cannot?
Yeah, the previous are just one statement, not
oh,
the
yeah,
question.
I think this is statement, not
Yeah,
question.
so probably, like to me, explain a bit more. That's just obviously with this silicon, with the high volume changes, so that's why we needed to make them in the nanoscales and to solve this problem.
Okay. So the next one, what is the role of carbon here, especially for the rice husk silicon carbon, I think, yeah. What is the role of carbon here, and is it as a metric for silicon dioxide, and also there is also a nitrogen dope, I think. So what is the role of nitrogen? Because normally we don't do any doping with nitrogen.
Yeah. So these are two questions actually. Okay. So carbon, carbon here in the final solution using biomass. So basically, otherwise, even with the artificial nanoparticles, we still need the carbon matrix to make anode materials. So you can't just use pure nanoparticles put in the anode. We still need some carbon to support them. That's the best way for manipulate or process the materials. And fortunately for the biomass, that's naturally happened during the process. So silicon nanoparticles or silica nanoparticles naturally embedded in the carbon matrix. And nitrogen here is tried to, we deliberately use nitrogen doping. We call it nitrogen doping. Basically, the purpose is try to make a more pores or improve the porosity in the materials. Related to the previous question, the porosity really play big role here in anode materials. So nitrogen doping here is just try, yeah, for simple answers, just try to improve the porosity.
Okay, okay. Okay, next question. Maybe this is it a must to dope the silicon dioxide carbon with nitrogen?
Yeah,
Maybe
that's
you have
related.
data, yeah?
Yeah, that's
With
related.
nitrogen,
Yeah,
what happened?
I presented the data to make a comparison. Yeah, well, you without a nitrogen doping, it still works very well and still
Okay,
achieves the very good results. But
all right.
with doping, you can improve that to the better performance.
Okay. Okay. Next question, Mr. Adi. The most difficult nanoparticles production is on both the mass scale and avoid the particles aggregation. How can you overcome both mentioned problem? I think with the functionalization, I think. Okay,
Right.
maybe you can answer.
Yeah, that's a very good question. Yes, yes, that's always happened in the lab. That these questions. These questions with me for the past 20 years. Yes, you need to think about how to make mass production and how to avoid aggregation as well. So always happened. And okay, so mass production, as I said, the top down, that's milligrams. Bottom up, you can go to kilograms. And now we're using biomass, natural materials, and we can make tons. That's a solution. And to avoid aggregation, really, using ligands to cap the surface, that would help a lot. And you need to choose ligands wisely. That's really, that's a very good question. But open to discussion would take days, weeks.
Okay, next question. Yeah. What is the most challenge in developing silica-based battery?
Oh, that's very good question. I don't have answer here, but a lot of challenges in the lab. People really busy to answer a lot of issues. So the most challenges, if I just pick one, really you need to think about during the charging, discharging, how to avoid degradations and avoid the damages of the anode. Yeah.
Okay. Next question. What are the advantage features of silica for battery?
Yeah. Okay. So yeah, probably you spotted that. As I said, you need to think about here when in the beginning I talk about silicon nanoparticles, and then move on to biomass. Obviously, from nature, most of them are silica, not silicon anymore. So yes, silica still got very high specific capacity. As I said, the theoretical value for silicon, that's 4,200, and silicon, basically we still can achieve 2,000. But in reality now, I presented data initial specific capacity. Some good ones, we can get the initial ones over 2,000. And then stable ones, now we achieved 800 or 900. Yeah, so that's that's similar to silicon. So don't have any other advantages over silicon, but that's a natural choice. We started with silicon and then natural choice for silica now.
Okay, next question. What is the most important feature of the material that can be used for developing battery?
Okay. So yeah, for anode, obviously, we need a higher capacity, the better. And yeah, in this talk, I just focused on anode. Obviously, if you look at other issues for batteries, and I briefly mentioned the electrolyte and the cathode, they got loads of issues as well. And so, yeah, if you read headlines from news every day, and probably you have this kind of related news every day and talk about battery development. Yeah, so yeah, if you just look at the materials, the capacity is the most important feature. And obviously you need to think about the lifetime, safety, and all these are important for batteries as well.
Okay, next question. How is the comparison between silicon-based battery with the others, such as a lithium-based battery? Is it more eco-friendly and cheaper, or any else?
Yes, you already pointed out that's environmentally friendly, very cheap, and in theory, obviously, silicon higher capacity over lithium. Another issue related to lithium is the safety issues. Yeah, remember, you heard a lot from news.
Yeah, explosion. Okay. Okay, next question. Okay, this is the last question, I think. How about friendly environmental issues when we compare with carbon batteries?
Yeah, that's a very good question. Yes, yeah, we really made that put that in consideration as well. We talk about silica nanoparticles from biomass. I say that this is environmentally friendly method, and also that's a green method. Wouldn't put any carbon footprint in the environment, and so that's I don't think we introduce any further issues if you just compare with carbon batteries. So don't have any other issues with our method.
Okay. Oh, I think still one question. What is the characteristic functional group embedded to silicon that obtain the best performance of the battery? What is the potential biomass to be silicon material?
Group. At the moment, we don't have any other artificial groups on the silicon particles. As I said, finally we just use biomass, and that's all natural. So we didn't introduce any other artificial functional groups, and potential biomass. We tried rice huskers and barley huskers because barley huskers, that's very popular in the UK, and rice huskers are popular in China. And other biomass, if you think about if they got a high percentage of silicon, and all these biomass would be potential choice. But you need to think about the other impurities, and are they harmful to batteries, etc. You need to think about that. In our process, remember, we got first step, we really need to wash them properly with acid, etc., to remove the impurities, etc. So all these details you need to think about. So otherwise, if you just think about what kind of biomass are used for, just think about the silicon content. That's the most important.
Okay. So there is no question anymore. So thank you very much, Dr. Yimin Chao, for this discussion and then sharing knowledge. I hope maybe in the future, after pandemics goes away, maybe we can visit the UK, or maybe you can come here as a visiting lecturer probably. So I hope we can have a collaboration in the near future.
Right. Okay. Thank you very much. You have me.
Okay.
Right.
Okay. So yeah. So thank you very much, everyone also here, and then see you next webinar series that will be held next month in the first week or maybe second week of September. So thank you again, Dr. Yimin Chao, and good morning over there and good afternoon over here. So goodbye and see you later.
Bye-bye.
Oh, sorry. Oh, maybe we can have a photo together before you leave. Take a picture. Okay. Mr. Adi, are you ready to take a picture?
Okay. 1, 2, 3. Okay. 1, 2, 3. Okay. Next. 1, 2, 3. Okay. Next. 1, 2, 3. Next. 1, 2, 3. Okay. Thank you.
Okay. So thank you very much, Dr. Yimin. Bye.
All right.
See you.
Bye-bye.
Bye. See you. Thank you, everyone.
Bye-bye.
Bye, Dr. Yimin. See you.
Oke, see you everyone. Terima kasih sudah datang. Kita ketemu lagi di seminar bulan depan ya, di minggu pertama atau minggu kedua.
Minggu kedua
ya. Oke.